Hi everyone, my talk is today on machine learning in HPC and how do we use TACC Supercomputers to solve machine learning. So a little bit about me before I begin. My name is Anusua Trivedi. I am a data scientist at Texas Advanced Computing Center, commonly known as TACC. TACC is an independent research center under UT Austin. It is one of the largest HIPAA-compliant supercomputer center. That means that we work a lot on healthcare data. There is about 250 people working for the lab, including faculty, researchers, students, and staff. We work on providing support to large-scale computing problems. Some basic observations in HPC has been there are fundamental differences in the data access patterns between data-intensive computing and high-performance computing, commonly known as HPC. Today, most of the machine learning researchers want to or need to work with big data, vectorization, code optimization, and many such problems. Let's go a little bit into the data-intensive computing. It is specialized in dealing effectively with vast quantities of data in distributed environments. It generates high demands for computational resources, like storing capacity, the processing power, etc. So how does big data and data-intensive computing coming together? How are they coming together? So big data plays the key role in the opportunity and growth of data-intensive computing. It has increased the volume of data we are used to. However, the volume of data improves the accuracy of the existing algorithms. It also helps us create better predictive models. In turn, however, it has also increased the complexity. So what's the challenge with the big data analysis? Let's explore a little bit on that. Big data analysis requires even more computational resources, like storage is triple the standard data size. Algorithms use a large number of data points and is memory intensive. Big data analytics takes much longer time. Typically, our hard drive read speed is about 150 megabytes per second, but for reading 1 terabyte, it would take you about 2 hours in a standard machine. Analysis could require processing time proportional to the size of the data that you're working on. Data analysis at the rate of 1 GB per second could require up to 11 days to finish 1 terabyte of data. Let's look a little bit into the high performance computing and how it is different than the data intensive computing that we just talked about. In HPC, hardware with more computational power per compute node is available. Computation can be done with multiple nodes. It provides highly efficient numeric processing in distributed environments. HPC has been doing it a long time even before the advent of Hadoop and Spark. HPC has seen a recent growth in the shared memory architectures. This is an example of a standard cluster in our TACC computing center. These on the left are the login nodes. If you log in through it, you will be put into the Scratch, which is shared with home, where you do all of your stuff. And from the Scratch and home both, you can actually access this multiple compute nodes. As you can imagine, because these could be imagined as a huge single machine, and it gets rid of the network problems, the data passing over network. So it gives much more advantage rather than traditional combined or network analysis. So let's combine HPC and data-intensive computing. The intersection of these two domains is mainly driven by the use of machine learning. Machine learning methodologies help us extract knowledge from big data. And these hybrid environments take the advantage of the data locality provided that I showed you in the last image, right? It takes advantage of the data locality. It keeps the data exchanges over the network at a manageable level. It offers high performance through distributed libraries. So many distributed libraries are available through HPC, and it actually gives you an advantage. So let's look a little bit into the TACC ecosystem. So we have multiple supercomputers. The most famous among them is Stampede, which is a traditional cluster HPC system. Actually, the main advantage of using our HPC, our supercomputers, is that you do not need to go in and spin up your own clusters. There is a GUI, a graphic user interface, presented to the users, and they need not take care of anything except mentioning the number of nodes they want to work with. So once you can go into the interface, you can actually specify the number of nodes you want to work with and the number of days you want your cluster to be available for, and then you spin up your own cluster. The machine at the back end actually spins up the cluster for you and helps you do your work without taking care of all the hardware and the library dependencies, everything like that. So Stampede is a traditional cluster HPC system with multiple nodes. You can assign up to 50 nodes there. Stockyard and Coral gives you 25 petabytes of combined disk storage for all the data needs. Ranch gives you about 160 petabytes of tape archive storage. Maverick, Rustler, and Rodeo are 3 independent machines which runs on GPU clusters, so it gives you advantage of using multiple GPU clusters, and it is great for data analytics and visualization kind of thing. If suppose you're wanting to do a CUDA-based deep learning stuff, I think Maverick or Rustler or Rodeo would either be helpful for doing that. A new kid in the block, a new supercomputer which we have launched and would be launching it in Supercomputing 15 is the Wrangler, a new generation of data-intensive supercomputer. It actually comes with installation of Hadoop and Spark, as well as a combination of Hadoop and Spark, which is run by Yarn. And it helps give us advantage of using HDFS and Spark. I'll talk a little bit more on how we are doing experiments using these machines. So let's look at the goals, what edge it gives you, the TACC ecosystem. The first goal is to address the data problem in multiple dimensions. It supports data in large and in small scales. It supports data reliability, data scalability, data security, and multiple types of data, structured, unstructured, different types. It is also supports data in sequential access, which is difficult to get in most of the machines. It is fast for a large number of files. The second goal is to support a wide range of applications and interfaces. So in our supercomputers, we have Hadoop and Moth and Spark and MLib installed. So you get to utilize the huge number of nodes in HPC by putting these libraries or tools on top of the nodes and running them. And the distributed thing, or the spinning up of the cluster, is taken care from the back end. All you need to think about is how you do your experiments, how you write your algorithms. The hardware stuff is taken care of by the interfaces from the back end. So the third goal is to support the full data lifecycle. It also has some databases and ETL tools. It helps you give the metadata and collection management support. So why would you want to use TACC supercomputers? In which cases should you be using such big machines? If you need to analyze large data sets quickly, that would be one example where you definitely want to use an HPC system. If you need more on-demand interactive analysis, if you need like real-time processing and interactive analysis, then definitely HPC is the way to go. If you need to work with databases at high transaction rates, if you have a Hadoop or Spark workflow with need for a large HDFS data store, if you have a data set with many users will compute with or analyze, so if you have multiple users working on the same nodes, on the same cluster, then definitely HPC would give you an advantage over it. In need of a system with data management capability, so we have our machines managing with ETL tools and stuff like that, so it helps you manage your data. You have a job that is currently I/O bound. So definitely if you get your interactions in live and streaming, so definitely that would help, like Spark streaming, things like that. So a few of the TACC success stories. So we have built a model for native and replacement heart valve to evolve human replacements. So we have a native and a human heart and a replacement valve, and we compare it to show that how heart replacements could be successful. We have UT Austin researchers find hotspots in genetic instability in cancer using Stampede and Lone Star. So there are these visualizations which helps you find the dark spot between which is a genetic instability using our high performance computing cycles. You can also build resources to calculate future damage from hurricane change. Our researchers have done that using the supercomputers and Exceed. There is great visualizations available. A new work based on 3D computer simulations of earthquake data has found hidden rock structures deep under the East Asia, which is helping geologists predict the earthquakes in those regions from a new perspective. We have also worked on forecasting, simulating seasons and the effect of it on a country's capability of growing crops. We have also applied them on political science and seen how spending affects a party polarization. So as you can see, that we have been working with in many domains, and we are actually handling from political science to healthcare to environment, everything. And TACC supercomputers are equally scalable and adjustable for all kinds of data. These are a few of the ML tools and libraries in TACC supercomputers which you can access. There is plain and simple MPI and CUDA-based CUDDN, CUDA-DDN, and for deep learning, there is Caffe, there is Theano, and I'll go a little bit into it through two samples. The first sample that sample workflow which I talk about is a GPU-powered deep learning on MRI images with NVIDIA digits on Maverick supercomputer. So we partner with MD Anderson Cancer Medical Center and some of other hospitals in Texas to get MRI images and build a predictive software system based on the MRI images. When stroke patients come first, they go through an MRI. Sometimes the doctor is not available to give the initial treatment. So we want to build a predictive software system where by reading just the MRI, initial treatment could be predicted for the patients, and it has actually shown us that these has actually led to more life-saving. The second system which I'll be talking about is a PubMed recommender system in another supercomputer. For the first one, I use Maverick supercomputer, which is mostly GPU-based cluster. And for the second, the PubMed recommender system, I use the New Kid on the Block, which is the Wrangler, which is the data analysis-based supercomputer. So deep learning on images for the MRI, deep neural networks are computationally quite demanding. The input data is much larger if we use even a small image resolution. So if you imagine 256 by 256 RGB pixel implies 196,608 input neurons. So that is how big it is. Many of the involved floating point matrix operation can be addressed by the GPU. So we actually utilize the underlying GPU cluster and run CUDA-DNN on it. So Maverick has large GPU clusters. There are three major GPU utilizing deep learning frameworks available: Theano, Torch, and Caffe. We use a Caffe-based method, which is the NVIDIA digits. It is a web server providing a convenient web interface for training and testing deep neural networks. So you do not have to do anything. You just have to load your files there. You do not have to take care of the algorithms. NVIDIA digits take care of it through Caffe. You can actually load your training file, your test file, and your labels, and it actually gives you the classification which you want to run on the images. For classification of MRI images, we use a convolutional DDN to figure out the features. So we do it through CUDA, so we use a CUDDN, which is a CUDA DDN. We use CUDA7, CUDDN, and Caffe and digits on Maverick to classify our MRI images. So on the course of 30 epochs, we do this iteratively, right? So over the course of 30 epochs, our classification accuracy ranges from 72% to 74% to 82%. So that's quite a decent way of getting data just out of MRI, not using any other external clinical data or anything. You're extracting all the features from the images, and you're classifying your MRIs based on whether the person has a stroke intensity of applying medicine or not applying medicine. So that was the GPU cluster example. Now we move on to the Wrangler example, where we create a recommender system for PubMed. Already in the morning, the speaker from Facebook have actually talked about recommender systems, so I would not be going into detail explaining it a lot. So recommender system helps match users with items. It's explicit user feedback or item suggestion. Our recommendation system, in our recommendation system, we tried to build a model which recommends PubMed documents to users based on a user search profile. So definitely there is a cold start problem there. You definitely, if you are applying collaborative filtering, you definitely need to have a user profile built up first. We have like 3 common types of recommended systems listed here, but I'm using collaborative filtering. So how do we get over the cold start problem for PubMed documents? We do not have any ratings available, right? It's just documents. So we apply an information retrieval method called the vector space model to actually weight and rank our documents based on the user's previous search history. So given is a set of PubMed documents and n features, which are unique terms describing the documents in the set. Vector space model builds an n-dimensional vector space. Each item or document is represented as a point in the vector space. So information retrieval is based on search. We take query as a point in the vector space. We apply TF-IDF technique to tokenize documents and weight the documents and convert the documents to vectors. We compute cosine similarity between the tokenized documents and the query term. We select top 3 documents matching our query, and that's how we create our user's profile. So suppose a user is searching about DNA. I would try to find out whether if they are interested in mouse DNA or human DNA. So over time, a user's profile will be built, and now if they go and search for DNA, if user A is interested in mouse DNA, they will be recommended mouse DNA related PubMed articles. If the user B is interested in human DNA, they will be recommended only human-related articles. So we weight the query term and the sparse matrix and rank documents. So now that we have our data ready, how do we actually create a recommender system in an HPC? So do we apply MPI or Hadoop or Spark, which is really more suitable for this ML problem in tackling in TACC Supercomputers? So let's look at that. So let's look at the message passing or the MPI. So message passing interface or MPI was one of the key factors which supported the initial growth of cluster computing. MPI helped shape what HPC world has become today. MPI supported a substantial majority of all supercomputing work. Scientists and engineers have relied upon MPI for the past decades. MPI works great for data-intensive computing in GPU cluster, as we just saw in the last example. However, why MPI is not the base tool for this ML workflow? A researcher or developer working with MPI needs to manually decompose the common data structures across processors. Every update of the data structure needs to be recast into a flurry of messages, syncs, data exchange, etc. Programming at the transport layer, where all these syncs and the message passing is happening, is an awkward fit for numerical application developers. It does not work very well if you're working on an iterative model, right? So messages being passed every iteration. It does not work very well for numerical application developers. This led to the advent of other techniques. Let's look at them. So let's think that if we are trying to choose Hadoop over MPI. So Hadoop is an open source Java implementation of MapReduce programming model. It has an interface to other programming languages such as R, Python. Hadoop includes HDFS, distributed file system based on Google Files. It also has a scheduler called Yarn. It is a resource manager to assign resources to computational tasks. It also has MapReduce capability, a library which enables efficient distributed data processing easily. It also has a machine learning library called Mahout. And it also has something called Hadoop streaming, which is a generic API which allows writing mappers and reducers in any language. Hadoop is a good fit for large-scale, single-pass data processing. If you're having a large amount of data, but you're not doing it iteratively, if it's a single-pass thing, then Hadoop is the best choice to go. But it has its limitation when iterations are involved. Limitations of Hadoop in HPC. Hadoop comes with mandatory MapReduce logging of output to the disk after every MapReduce stage. In HPC, logging output to disk could be sped up by caching or SSDs. So we can actually speed up this logging speed, but we cannot absolutely avoid it. In general, this fact rendered Hadoop unusable for many machine learning approaches when required iteration on interactive use. The real issue was with Hadoop being tied very tightly with its file system, which is HDFS. The large-scale machine learning community, that's why, sought after in-memory approaches to avoid this iteration problem. So Spark is a large-scale technical computing. For large-scale technical computing, one very promising in-memory approach is Spark. Spark lacks MapReduce style requirements. Spark can run standalone without a scheduler like Yarn. It has interfaces to other programming languages such as R and Python. Spark supports HDFS. So the one which I will be using for my example is Spark through HDFS, Spark supporting HDFS through Yarn. It has got a machine learning library called MLlib. And there is something called Spark streaming, which enables stream processing of live data streams. Let's look at our recommendation model. We apply collaborative filtering on the weighted and ranked documents. So we have weighted and ranked the documents using vector space model, and we are applying collaborative filtering on it. So we use so we actually use the alternating least squares, which was talked about today, for recommending PubMed documents in Spark. So for Spark, I am using PySpark interface, something in Python, and through that MLlib, I'm using the alternating least square method. We use collaborative filtering in scikit-learn and Hadoop as baselines. So we use, we are trying to compare the performance of Spark in TACC Supercomputers compared to scikit-learn and Hadoop. So for working with scikit-learn, we use a library called Python Rexus. It goes through the SVD recommendation technique, and that's how we create one baseline through it. The second one is Mahout's alternate least square for Hadoop, which is very similar to the Sparks, and we have Hadoop as another baseline. So a comparative study of our model shows improved performance in Spark. Let's look at it. We evaluate our recommendation model using Python scikit-learn, Apache Mahout, and PySpark MLlib in Wrangler. So we are using Wrangler Supercomputer for doing this. Our recommendation model use root mean square error, which is RMSE, and mean absolute error, which is MAE, which gives you actually how good the recommendation techniques are. Root mean square model gives you the accuracy of the model. Mean absolute error gives you the accuracy with which you are recommending. So it's essential to look at both of them for evaluation purposes. So lower the errors are, more accurate the models are. Lower the time taken to train or test the model, better the performance. So in this table, we see that we have three libraries working on the weighted PubMed documents. And the first one is the Python scikit, the second is Apache Mahout for Hadoop, and the third one is PySpark MLlib. We see that as the dark block, if you see the dark block, the error is going down, and the training time is also going down. Thus, we can say that in our TACC Supercomputers, Spark MLlib works better than traditional Python cases like using scikit-learn or than using Hadoop. So that was my talk, and just an example of showing how you could apply your own data and do some data cleaning and build a recommendation model, how to do deep learning using CUDA. And if you have more questions or would like to collaborate with us, with TACC, and utilize all these abilities of the TACC Supercomputers, please connect with me, and I'll be available to talk over lunch. Thank you.